You are on the edge of something so powerful. Time slows down around you. Light can't escape, and the rules of reality begin to twist. You're not in a sci-fi movie. This place exists. It's a black hole. And once you understand what it really is, you'll never look at the universe the same way again. So buckle in, because you're about to fall into one of the greatest mysteries in all of science, and you might not come out thinking the same. Black holes are among the most mysterious and captivating objects in the cosmos. The term black hole alone sparks intrigue. In fact, it's one of the highest searched astronomy topics, reflecting our fascination with these extreme gravity phenomena. But what exactly is a black hole? Despite the name, it isn't an actual hole or empty space. Rather, a black hole is an astonishingly dense concentration of matter packed into a tiny region. Its gravity is so powerful that beyond a certain boundary, known as the event horizon, nothing can escape, not even light. This gravity trap is what makes a black hole black, as light crossing the event horizon can never return. Yet, black holes aren't completely invisible voids. We'll see that they often reveal themselves through their dramatic effects on their surrounding matter. In this script, we'll journey through the world of black holes in a clear and conversational way. We'll explore how black holes form, their mind-bending properties, the different types that exist, and how scientists detect these invisible beasts. We'll also delve into the strange effects black holes have on their surroundings, from warping light to slowing time. Discuss intriguing theoretical ideas like Hawking radiation and the information paradox, and clear up some common misconceptions. By the end, you'll understand why black holes are not just cosmic oddities, but also crucial laboratories for physics and a continual source of wonder for scientists and the public alike. So let's dive into the gravity well. Black holes may be mysterious, but we have a pretty good handle on how many of them are born. The most common pathway is through the death of massive stars. When a star much more massive than our Sun, typically greater than 8 to 10 times the Sun's mass, runs out of nuclear fuel, it can no longer support itself against gravitational collapse. The star's core implodes in a spectacular supernova explosion, and if enough mass crams into a small enough space, the core collapses into a black hole. This is how a stellar mass black hole is formed. Essentially, a stellar corpse, only a few times the Sun's mass, compressed into an incredibly dense state. Less massive stars, by contrast, end up as neutron stars or white dwarfs, not black holes. Another route to forming a black hole is through extreme collisions and mergers. For example, when two neutron stars, the dense remnants of smaller supernovae, crash into each other, their merger can create a black hole. This scenario isn't just theoretical. It was observed in 2017 when LIGO and Virgo detected gravitational waves from a neutron star collision that likely produced a black hole. Similarly, two existing black holes can merge to form a larger one, An event also detected via gravitational waves in 2015. More on that later. Before we continue the story, make sure to like and subscribe so you don't miss more interesting bedtime stories to accompany your sleep.
In the early universe, black holes might have formed in other exotic ways. One idea is the direct collapse of massive gas clouds before stars even formed. If a huge cloud of primordial gas collapsed under its own gravity, it could skip the star stage and create a black hole of perhaps 1,000 to 100,000 solar masses, a seed for the supermassive black holes we see in galaxies. And there's even a hypothesis that primordial black holes could have formed just after the Big Bang. As space expanded rapidly, dense fluctuations might have been squeezed into tiny black holes, perhaps with masses far smaller than the Sun. These primordial black holes remain hypothetical. We haven't found definitive evidence for them, but they represent another possible formation channel for the very smallest black holes. In summary, black holes can be born in several ways: the collapse of massive stars, collisions or mergers of stellar remnants, direct collapse of early universe gas, and maybe even primordial events in the young cosmos. Whatever the mechanism, the end result is the same: matter crammed into a volume so small and dense that a gravitational trap is formed. Black holes push physics to their limits, and their properties sound almost like science fiction. Let's break down some key features of a black hole's anatomy and behavior. Event horizon. This is the defining surface of a black hole, the invisible boundary around the black hole beyond which nothing can return. You can think of the event horizon as the point of no return. Inside it, the escape velocity exceeds the speed of light, meaning not even light can get out. That's why black holes are black. If anything, a star, a spaceship, even a ray of light passes this boundary, it's doomed to be pulled inward. From the outside, we can never see past the event horizon. Any information from inside is essentially cut off from our universe. The event horizon isn't a physical surface you could touch. It's just a region in space defined by gravity. Still, we often imagine it as the surface of the black hole for simplicity. The size of the event horizon, often called the Schwarzschild radius for non-spinning black holes, depends on the black hole's mass. For example, a black hole with the mass of our Sun would have an event horizon only about 6 kilometers, about 4 miles across, incredibly small for an object containing a whole Sun's worth of mass. Supermassive black holes have larger horizons. The one at the center of M87 spans roughly 40 billion kilometers, but even that is just a fraction of our solar system. Singularity. At the very center of a black hole, according to Einstein's general relativity, lies the singularity, a point or region where the density becomes infinite and the known laws of physics break down. It's the final destination for anything that falls in. In the classical picture, all the black hole's mass is crushed into this infinitely small point. However, infinite density is a huge red flag that our physics is incomplete. It likely means we need a theory of quantum gravity to really understand what happens in that core. Is the singularity a literal point of infinite density, or is it just our equations going haywire? At the moment, astronomers and physicists aren't sure. The prediction of a singularity signals the limits of general relativity. We expect that quantum effects, which aren't included in relativity, would become important at such extremes. In essence, the singularity is a mystery zone where our current theories falter.
Mass and spin. No hair properties. Remarkably, black holes are simple in terms of their measurable characteristics. A famous idea in physics, the no-hair theorem, says that a black hole, in general relativity, can be completely described by just a few parameters. mass, spin, and electric charge. Astrophysical black holes are expected to have neutral charge. Any charge would attract the opposite charge and quickly cancel out. So in practice, it comes down to mass and spin. That's it. All the complex details of whatever formed the black hole, whether it was a star, gas cloud, etc., are forgotten once it becomes a black hole. Only the mass and rotation remain imprinted. This makes black holes almost elegant in their simplicity. Two black holes with the same mass and spin are essentially indistinguishable, even if one formed from a star collapse and the other from a neutron-star merger. The mass determines the gravity and size of the event horizon, and the spin affects the black hole's shape and how space-time is dragged around it. A fast spin can actually make the event horizon slightly smaller, and in theory, spinning black holes could possibly have some weird effects like frame dragging and ergospheres, but those details are beyond our scope here. The key point: unlike, say, stars, which have many properties, size, temperature, composition, etc., a black hole is defined by just a couple of numbers. Gravity and tidal forces. A black hole's gravity is extreme. What makes it special isn't that it's some kind of magic vacuum cleaner, but that you can get very, very close to all that mass. Gravity's strength increases as distance decreases. Because a black hole's mass is packed so tightly, you can approach it to within a few kilometers, at which point the gravitational pull is enormous. Close to the event horizon, space and time themselves are being warped drastically. Tidal forces, the difference in gravity's pull on the near versus far side of an object, become devastating. Near a small black hole, the gradient is so steep that it can stretch and strip apart objects. More on this spaghettification in a moment. Yet from afar, a black hole's gravity is no different than any other object of the same mass. Replace our sun with a one solar mass black hole, and Earth's orbit would remain unchanged, aside from the lack of sunlight. This is an important clarification. Black holes don't pull at things at long range any more than, say, a star or planet does. It's only when you venture very close that their gravity gets weirdly intense. These properties paint a picture of a truly exotic object, an ultra-compact mass with an invisible boundary and a mysterious center, characterized simply by how heavy and how fast it spins. Everything about a black hole is extreme, yet in many ways it's also a surprisingly simple entity defined by fundamental physics. Not all black holes are the same. Astronomers classify them by mass and by how they likely formed. Here are the major types of black holes we know or theorize about. Stellar mass black holes. These are the small black holes formed from collapsing massive stars. They typically have a mass of a few times, up to perhaps dozens of times, that of our Sun. A classic example is Cygnus X1, one of the first black hole candidates discovered in the 1960s, which is about 15 solar masses. Stellar black holes are common. Scientists estimate our Milky Way galaxy alone may harbor tens of millions of them. However, they're hard to detect unless they interact with other stars or gas, because a lone black hole in space is practically invisible. Often, a stellar black hole in a binary system will pull gas from its companion star, forming a hot X-ray emitting accretion disk that gives it away. These black holes are like the corpses of big stars, and LIGO's first gravitational wave detection in 2015 was actually from two stellar mass black holes, around 36 and 29 solar masses, merging into one.
Supermassive black holes. At the opposite end of the spectrum, we have the giants. Supermassive black holes weigh in at millions to billions times the mass of the sun. And where do we find these monsters? At the centers of galaxies. Virtually every large galaxy, including our own Milky Way, has one. The Milky Way's central black hole, Sagittarius A, is about 4 million solar masses. An even bigger example is the black hole in galaxy M87, which is 6.5 billion solar masses. That's the one famously imaged by the Event Horizon telescope. Supermassive black holes didn't form from single stars. No star could get that big. They likely grew over billions of years by gobbling gas, merging with other black holes, and perhaps starting from large seed black holes in the early universe. When actively feeding, these behemoths power quasars and active galactic nuclei, shining brighter than entire galaxies. Despite their huge mass, their density can be lower than stellar mass holes because their event horizon radius scales with mass. For instance, the Schwarzschild radius of a 4 million solar mass black hole, Sag A, is about 12 million kilometers, large enough to fit within Mercury's orbit. Supermassive black holes are central to galaxy evolution. Interestingly, there's evidence that the growth of a galaxy's central SMBH and the galaxy itself are linked. Intermediate mass black holes. These are the middleweight category, and they've been somewhat elusive. Intermediate mass black holes, IMBHs, would be heavier than stellar black holes, say 100 to 100,000 solar masses, but not quite supermassive. For a long time, we had only hints they might exist, too massive to come from one star, too small to be the monsters in galactic cores. Recent evidence is mounting for IMBHs. For example, observations of certain star clusters suggest a black hole of a few thousand solar masses may lurk there. In 2020, LIGO detected a merger that produced a black hole around 142 solar masses, which was the first strong confirmation of an intermediate mass black hole formed by stellar mergers. There have also been X-ray sources and galaxy observations hinting at IMBHs. They might form through repeated mergers or from early universe stars that were unusually large. IMBHs could be the missing links that help explain how supermassive black holes got so huge, perhaps by merging smaller ones. They're active areas of research, kind of the teenagers of the black hole family that we're just getting to know. Primordial black holes. This type remains speculative, but it's fascinating to consider. Primordial black holes would be tiny black holes formed not from stars, but from high-density fluctuations in the very early universe, fractions of a second after the Big Bang. If certain regions of the infant universe were dense enough, they could collapse into black holes weighing maybe as little as an asteroid or as much as a mountain. Because they didn't come from stars, these black holes could, in theory, have any mass,
even much less than the Sun. Stephen Hawking and others proposed that such miniature black holes might have formed, and that they could even make up some part of the dark matter puzzle. However, if they were very small, Hawking radiation would cause them to evaporate over cosmic time. The smaller the black hole, the faster it evaporates. Tiny ones might be long gone by now. So far, we haven't found conclusive evidence of primordial black holes. We've set limits based on things like gravitational lensing surveys and cosmic gamma-ray background. Evaporating black holes would produce bursts of high-energy radiation. If any primordial black holes still exist, they'd be very hard to detect, but the search continues. Some scientists have even wondered if unusual events detected by gravitational wave observatories could be primordial black holes colliding, but the jury is still out. In summary, black holes come in a cosmic size chart from the stellar mass small fry to the supermassive titans, with a possible intermediate class in between. There may have even been tiny primordial ones in the early universe. Each type plays a different role in the cosmic story, but all share the same basic nature: a region of space where gravity reigns supreme and normal physics takes a backseat. If black holes themselves emit no light, since light can't escape their grasp, how on earth do we know they're out there, let alone study them? It turns out black holes leave plenty of clues for clever astronomers to detect. Here are some of the key ways we find and observe black holes. 1. Accretion disks and electromagnetic emissions. Most black holes, especially if they're actively feeding, are not actually black at all. They're surrounded by swirling disks of infalling gas and dust that can glow brilliantly. As matter spirals into a black hole's gravity well, it forms an accretion disk. Think of water spiraling down a drain, except it's superheated plasma orbiting a black hole. Friction and turbulence in the disk heat it to extreme temperatures, so it shines in X-rays, ultraviolet, and other wavelengths. These X-ray or radio emissions are often the first sign of a black hole. For example, Cygnus X1 was discovered by its X-rays. It's a black hole pulling gas off a companion star. Black holes can thus paradoxically become some of the brightest objects in the sky, in X-ray or radio, thanks to their glowing disks. In addition, some black holes, especially supermassive ones, produce jets, narrow beams of particles and energy shooting out from the poles at near light speed. These jets, which can emit radio waves and even gamma rays, are associated with black holes at the centers of active galaxies, quasars or blazars. So, a lot of black hole hunting boils down to looking for these telltale signs: X-ray flashes, radio jets, or other emissions that point to a massive, compact object accreting matter. 2. Stellar motions and orbits. Another way to see a black hole is by its gravitational influence on visible objects. If a star appears to be orbiting an invisible partner, that partner might be a black hole. In our own galaxy, astronomers observed stars near the Milky Way's center whipping around an unseen object at high speeds. By tracking these stellar orbits for years, they concluded there's a supermassive black hole, Sagittarius ACE*, of 4 million solar masses lurking there. A discovery so significant it earned the 2020 Nobel Prize in Physics. Essentially, we infer the black hole's presence from the dance of stars or gas around it. Even for stellar mass black holes, if one is in a binary system, the companion star's motion, wobbling due to the black hole's gravity, can reveal the black hole. We can use Newton's laws or relativity to calculate the mass required to cause such orbits. If the mass is high and no light is seen from it, a black hole is the prime suspect. Observatories like the Keck telescope and ESO's Very Large Telescope have taken images of the galactic center showing stars making elliptical orbits. The only thing compact enough and massive enough to explain those orbits is a black hole. This method is basically detecting black holes by the gravitational pull they exert on their environment. 3. Gravitational waves. In recent years, we've opened a whole new ear on the cosmos, listening for the ripples in space-time called gravitational waves. When massive objects, like black holes, collide or merge, they literally shake the fabric of space-time, sending out gravitational waves that can be detected by sensitive instruments on Earth. In 2015, the LIGO Observatory made the first historic detection of gravitational waves, and it turned out to be two black holes merging about 1.3 billion light-years away. This discovery was groundbreaking. Not only did it prove Einstein right, he predicted gravitational waves a century ago, but it also confirmed the existence of heavy, stellar mass black holes that we hadn't seen before. The merging black holes were around 30 solar masses each, larger than any known neutron star. Since then, dozens of black hole mergers have been heard by LIGO and Virgo. We're basically eavesdropping on black holes as they in-spiral and collide. Gravitational wave detection doesn't see the black hole directly, it's more like feeling the tremor of a distant catastrophe. But from the waveform, scientists can infer the masses and spins of the black holes involved. Excitingly, gravitational waves have also caught the merger of a neutron star with a black hole, and possibly the formation of intermediate mass black holes. This method is revolutionizing astronomy because it allows us to find black holes that emit no light, dark mergers in the void. It's akin to having a new sense. We can hear the universe's most violent events.
4. Direct imaging. The Event Horizon Telescope. One of the most stunning recent developments is that we have actually imaged a black hole's immediate vicinity. In 2019, the Event Horizon Telescope collaboration released the first ever photograph of a black hole shadow, the supermassive black hole at the center of galaxy M87. This was followed in 2022 by an image of our Milky Way's own Sagittarius A. How is this done? The EHT isn't one telescope, but a network of radio telescopes across the globe, synchronized to act as one giant Earth-sized dish. It targets the extremely compact radio emission around the black hole, the inner accretion flow, and reconstructs an image with incredible resolution. The result for M87 was that iconic ring of fire, a glowing donut shape, where the dark center is the black hole's shadow, caused by the event horizon's gravity trapping light, and the ring is light from the hot gas just outside the horizon. This image beautifully matched what physics predicted, a circular silhouette about 40 micro-arc-seconds across. Seeing that ring was a powerful confirmation of black hole theory and general relativity. It was literally seeing the unseeable. Direct imaging is so far only possible for the largest black holes, M87, Sagittarius A, but it's a technique that will improve, and future arrays might even make movies of gas swirling around a black hole, or capture images of smaller black holes. The EHT images thrilled scientists and the public alike. a moment where something that had lived in our imaginations became visibly real. In addition to these methods, there are other clever tricks. For example, gravitational lensing, where a black hole's gravity bends the light of a background star, can reveal a black hole. This is being used to hunt isolated black holes in our galaxy via micro-lensing surveys. Also, sudden high-energy flashes can indicate a star was torn apart by a lurking black hole, a tidal disruption event. We truly have a diverse toolkit to find black holes. Often it's about observing the effects a black hole has on its surroundings, whether it's stirring up stars, heating gas to shine, or merging and ringing space-time like a bell. Despite their dark nature, black holes are far from hidden to those who know how to look or listen. The first ever image of a black hole's shadow, captured by the Event Horizon Telescope in 2019. This supermassive black hole, 6.5 billion suns in mass, lies at the center of galaxy M87. The bright ring is light from hot gas swirling just outside the event horizon, and the dark central region is the silhouette where light is captured by the black hole's gravity. Black holes don't just sit quietly. They dramatically affect their environment. Their gravity is so extreme that it can distort space, time, and matter in extraordinary ways. Let's explore a few of the wild effects a black hole has on its surroundings. Gravitational lensing, bending light. Gravity can bend the path of light, a prediction of Einstein's general relativity that black holes showcase spectacularly. Around a black hole, space-time is curved like a funnel. Light passing near the black hole will follow this curved space, causing it to veer from a straight line. To an observer, this looks like the light has been bent, similar to how a glass lens bends light. If a black hole passes in front of a distant star or galaxy, it can actually lens the light and produce weird visuals. The background object might appear distorted, multiplied, or as a ring around the black hole. In the case of a black hole with an accretion disk, gravitational lensing can make the far side of the disk visible above and below the black hole, creating that double hump image we discussed. In effect, the black hole's gravity acts like a cosmic funhouse mirror, or lens, warping the appearance of anything behind it. Astronomers use gravitational lensing as a tool. For instance, micro-lensing events where a star's brightness spikes because a massive compact object passed in front and lensed it can hint at an unseen black hole or planet. One famous demonstration of gravitational lensing by a black hole is actually in the movie Interstellar. The visuals of the black hole, Gargantua, with a halo of light, were inspired by real lensing calculations. Physicist Kip Thorne worked on those. So a black hole literally bends the light around it, sometimes allowing us to see things that would be hidden and confirming that gravity indeed affects light as predicted. Time dilation, slowing time to a crawl. If you think bending space is crazy, black holes also mess with time. According to relativity, time runs slower in stronger gravitational fields. This is called gravitational time dilation. Near a black hole, the effect is severe. Imagine our brave, but hypothetical, astronaut friend Alice falling toward a black hole while her twin Bob watches from afar. From Bob's perspective, as Alice gets closer to the event horizon, her clocks tick slower and slower. In fact, he would see her approach the event horizon ever more slowly and never quite falling in. She would appear to freeze at the edge, fading as the light redshifts, but never disappearing completely. Meanwhile, Alice, as she falls, feels time normally for herself. She crosses the horizon and heads toward the singularity in a finite time, and presumably meets a nasty end. This isn't just sci-fi. Time dilation near black holes has observable consequences. For instance, the photons escaping from near the event horizon lose energy. Their wavelength gets stretched due to time dilation and gravity. That's gravitational redshift, which has been measured. The idea that time can stretch is hard to wrap our heads around, but it's a real effect. Clocks near Earth's surface tick a bit slower than clocks in GPS satellites high above because Earth's gravity causes a tiny time dilation. Black holes magnify this to an extreme. If you orbited near a black hole for what you felt was 1 year and returned, far more time could have passed in the outside universe, a plot point also used in Interstellar. In short, a black hole is not just a gravity well, but a time machine of sorts, a one-way trip forward for anything that gets too close, since time for that object relative to the outside world will be hugely dilated. But fair warning, it's not a usable time machine for coming back or visiting the future and returning. Once you're that deep in, you're not coming out. Tidal forces and spaghettification. We mentioned earlier that black hole tidal forces can stretch things out. Now let's really picture it. Suppose an unlucky star or astronaut gets too near a black hole. The gravity pulling on the side of the star closer to the black hole is much stronger than the pull on the far side. This difference is the tidal force, and as the star gets closer, the difference grows. The result can be catastrophic. The star is pulled apart into a long stream. Stephen Hawking famously dubbed this stretching to the extreme spaghettification, because any object would be stretched into a long, thin shape like spaghetti by the black hole's gravity. In Hawking's A Brief History of Time, he imagined an astronaut getting stretched into a strand. For small black holes, spaghettification would rip you apart even before you reach the event horizon. Tidal forces increase the closer you get to, and small black holes have very steep gravity gradients near the horizon. For supermassive black holes, interestingly, you could cross the horizon before tidal forces become lethal, because the gradient at the horizon is gentler, but ultimately the singularity's pull will get you. Astronomers have observed what they call tidal disruption events, where a star wandering too close to a galaxy's central black hole gets torn to shreds. We see a sudden flare as the star's gas is heated and devoured. One cool simulation shows stars being stretched into noodle-like strands by a 1 million solar mass black hole. On top of that, supermassive black holes can also flatten stars by tidal forces in a process whimsically termed pancake detonation, where the star is squashed and triggers a thermonuclear explosion. So whether spaghetti or pancakes, the menu is not friendly to objects near a black hole. This is a vivid reminder that straying too close to a black hole is a terrible idea. The tidal forces will distort, shred, or compress matter in spectacular ways. These extreme interactions also give off lots of radiation, which is how we detect them.
Influence on galactic scales. Feedback. Black holes, especially the supermassive ones, can influence regions far beyond their event horizons through what scientists call feedback. When a supermassive black hole feeds on large amounts of gas, it doesn't swallow it all quietly. A lot of that energy gets released back into the surroundings. The accretion disk can heat gas to millions of degrees, causing powerful winds,
and the black hole can launch jets that shoot out of the galaxy's center. These jets and winds can blast material outward across tens or even hundreds of thousands of light years. It's like the black hole is a cosmic engine. While gobbling some fuel, it's also spitting some out violently. This can affect star formation in the galaxy. For instance, the outflows might blow away the gas that would have otherwise cooled and formed new stars, thus suppressing star birth. In other cases, the shock waves might compress gas clouds and stimulate star formation. Astrophysicists have realized that to understand why galaxies look the way they do, we have to account for their central black holes. They are not just passive diners, they can be messy eaters, and the mess they create can heat or redistribute gas in the galaxy. This helps explain, for example, why we don't see too many overly massive galaxies. A fiercely feeding central black hole might have blown out the gas and stopped the galaxy from making more stars. Our Milky Way's black hole is fairly quiet now, but we see evidence of past activity, like the Fermi bubbles, giant gamma-ray emitting bubbles, possibly from an ancient jet. In summary, black holes can shape their cosmic environment, playing a key role in galaxy evolution. They're not just passive sinks, they can also energize and sculpt the space around them through their formidable gravity and the energetic fireworks that accompany their feeding. In all these ways, bending light, warping time, shredding matter, and driving cosmic feedback, black holes demonstrate that they are anything but innocuous. They are engines of extreme physics, and their presence leaves an unmistakable imprint on the universe around them. Black holes don't just challenge our engineering to detect them, or intuition. They also pose deep theoretical puzzles that physicists are still trying to solve. Some of the most interesting concepts in black hole physics include Hawking radiation. Black holes can evaporate. In the 1970s, physicist Stephen Hawking made a startling prediction. Black holes aren't completely black. By applying quantum mechanics to the space just outside the event horizon, he found that black holes should slowly emit radiation, now called Hawking radiation. Here's a hand-wavy way to think of it. In quantum physics, empty space isn't truly empty, but teems with virtual particle-antiparticle pairs popping in and out of existence. Near the event horizon, one of these particles could fall into the black hole while the other escapes before they annihilate. The escaping particle carries away energy, which to an outside observer looks like the black hole is emitting particles, or thermal radiation. To conserve energy, the particle that fell in effectively has negative energy relative to outside, reducing the black hole's mass. Over enormous timescales, this leak of radiation will cause the black hole to lose mass and eventually evaporate in a final burst of energy. This idea was radical because it united gravity, quantum mechanics, and thermodynamics, showing black holes have a temperature and entropy. One practical implication: black holes aren't eternal. If Hawking was right, given enough time, they fizzle out in a final burst of energy. This idea is widely accepted in theory, though Hawking radiation is too faint to observe for any known black hole. It's an incredible thought. Something once considered the ultimate sink can actually give back a little energy to the universe. Hawking radiation also implies black holes have entropy and temperature, bridging a gap between gravity and thermodynamics. It's one of the first clues toward a possible quantum theory of gravity.
The information paradox. Hawking radiation opened a can of worms in theoretical physics. If a black hole can evaporate away completely, what happens to all the information about the stuff that fell in? In quantum physics, there's a fundamental principle that information cannot be destroyed. You should, in theory, be able to trace outcomes back to initial conditions. But a black hole that evaporates seems to erase the details of everything it swallowed, because Hawking radiation, as Hawking calculated, carries no detailed imprint of the infalling matter. It's basically just thermal noise, dependent only on the black hole's mass, spin, and charge. This is the black hole information paradox. General relativity says information that falls into a black hole is lost to the outside universe, and if the black hole disappears, that information is gone for good. While quantum theory says information can't just vanish. These two pillars of physics are in direct conflict here. The paradox has led to decades of research and debate. Hawking himself bet that information was lost, but many physicists suspect that somehow, in the full theory of quantum gravity, information is preserved, perhaps encoded in subtle correlations in the Hawking radiation, or stored in a holographic way on the event horizon. Proposed resolutions include the idea of soft hair on black holes, quantum imprint on the horizon that carries info, or the ER equals EPR conjecture, linking wormholes with quantum entanglement. Or more exotically, that what we think of as a black hole might not be what's really there at the deepest level. In 2012, some researchers suggested a firewall, that the interior of the black hole might not be smooth, and anyone falling in hits a wall of high-energy quanta, which could resolve info loss, but at the cost of contradicting relativity at the horizon. Others have developed string theory models where the black hole is replaced by a tangle of strings or fuzzballs that have no singularity and do not destroy information. A recent idea is the quantum hair theory, where black holes do retain a subtle signature of what falls in. Even more recent, 2020's proposals suggest black holes might be something like frozen stars, exotic compact objects without true event horizons or singularities, thus sidestepping the paradox. The jury is still out, but most physicists believe that a correct quantum theory of gravity, perhaps via string theory or loop quantum gravity, will eventually show how information escapes or is preserved. The information paradox is essentially a clash of titans. You've got to modify something in our understanding, either quantum mechanics or relativity or both, to resolve it. This makes black holes crucial testing grounds for new physics. They sit at the nexus of quantum theory and gravity, our two best yet fundamentally inconsistent frameworks of nature.
Quantum gravity and the end of the singularity. As mentioned, the singularity in a black hole signals a breakdown of known physics. Many theoretical physicists suspect that when we have a full quantum theory of gravity, singularities will be resolved into something more physical, no infinities. For example, in some quantum gravity models, the core of a black hole might be a super-dense nugget of quantum matter, not an infinite pit. Some speculative ideas, a black hole might eventually transition into a different object, a Planck star or a baby universe, or maybe at the very end of evaporation, it explodes, releasing information. Another idea is that black holes and white holes, time-reversed black holes where nothing can enter, only leave, could be connected, or that at the singularity, perhaps a bridge, wormhole, forms to another patch of the universe. Though traditional wormholes aren't stable, some theories toy with this. These are highly theoretical and not established, but they illustrate how black holes drive frontier research. Every quantum gravity theory, be it string theory, loop quantum gravity, etc., tries to make sense of black holes in a way that removes the singularity and preserves cosmic bookkeeping of information. Solving these riddles could lead to new physics that unifies the quantum and the cosmic. In essence, black holes are laboratories for quantum gravity, extreme conditions where our current theories don't agree, thus providing vital clues for the next breakthrough. Recent breakthroughs. The past decade has been monumental for black hole research. We've had direct confirmation of long-held theoretical predictions. Gravitational waves from black hole mergers proved black holes in binary systems and gave insights into their spins. The EHT images confirmed that the event horizon and shadow align with general relativity's expectations of a circular silhouette. On the theoretical side, there have been intriguing developments. In 2019, Hawking's former collaborators proposed a solution to the information paradox involving soft hair on black holes, essentially subtle quantum imprints on black holes. In 2022 to 2023, there were studies using the idea of entanglement islands from quantum information theory that hint information might escape in Hawking radiation after all by a complex mechanism. And as mentioned above, some physicists are exploring alternatives like black hole mimickers, the frozen star concept from 2024, or gravastars, etc., that might avoid paradoxes. While none of these are confirmed, it's an exciting time. We're actually testing theories against real data from EHT and LIGO. Even the fact that gravitational waves matched Einstein's relativity so well places limits on crazy new physics. For example, the black hole mergers didn't show obvious signs of exotic event horizons, which might mean no firewalls, at least not for those cases. There's also ongoing research into phenomena like Hawking radiation analogs in the lab, using things like sonic black holes in fluids to simulate event horizons and see Hawking-like emission. All told, the theoretical landscape is rich and evolving. Black holes haven't given up all their secrets. They likely have more surprises in store that could revolutionize our understanding of physics. In sum, black holes aren't just astrophysical objects. They're also crucibles for fundamental physics. Hawking's revelation that they can evaporate blurs the line between thermodynamics and gravity, leading to the infamous information paradox that challenges our understanding of reality at a fundamental level. As research marches on, every new observation, a merger ring-down waveform, a sharper image of a black hole's shadow, etc., and every new theoretical insight, be it a proposed paradox solution or a quantum gravity model, takes us a step closer to grasping one of nature's most profound enigmas. The story is ongoing, and that's what makes black hole physics so thrilling.
Black holes captivate the public imagination, but they also invite a lot of misconceptions. Let's clear up a few popular myths and misunderstandings about black holes. Black holes are cosmic vacuum cleaners that suck up everything in space. This is probably the most common myth. It conjures an image of a black hole roaming around, hoovering up matter willy-nilly. In reality, a black hole's gravity works just like the gravity of any other object of the same mass. If our sun were suddenly replaced by a black hole of equal mass, the Earth and other planets would continue orbiting in the same way. They wouldn't get sucked in. We'd have no sunlight, which is a problem, but gravity-wise, nothing changes at a distance.
You have to get very close to a black hole for the extreme effects, like being spaghettified or not being able to escape, to kick in. Black holes don't reach out with a vacuum force. They simply sit there, obeying gravity. So objects can, and often do, orbit around black holes stably. Matter has to lose energy, for example, via friction in an accretion disk, to spiral in. In short, black holes are not space Roombas. If you keep a respectful distance, you won't fall in. They're dangerous in close proximity, but they don't actively seek out stuff to consume. Our sun could turn into a black hole and destroy the Earth. Fear not, our sun is far too small to become a black hole when it dies. Only stars with much greater mass go supernova and potentially form black holes. The sun will eventually become a red giant and then a white dwarf, but never a black hole. Even if by some magic the sun were replaced by a one solar mass black hole, as mentioned above, our Earth's orbit would remain the same. We'd actually be farther from that black hole's event horizon, 3-kilometer radius, than we are from the sun's surface now. So we'd be in no danger of being pulled in. The Earth would get very cold and dark, but not plummet into the black hole. So, there's no risk of a spontaneous black hole apocalypse for the Earth via our sun. Black holes are born from massive stars many times the sun's mass. Fortunately, there are none of those extremely close to us. Black holes are holes in space, or wormholes to another dimension. The term black hole is a bit misleading because it's not a hole through which you go somewhere else. It's an object, a very dense mass in space. It's called a hole because things that go into it don't come back out, not because it's a tunnel. In science fiction, black holes are sometimes depicted as gateways to other universes or as passages for time travel. While some speculative physics ideas connect black holes and wormholes, a wormhole is like a shortcut through space-time that might connect two distant regions. There's no evidence that the black holes we know function as wormholes. The general solution for a non-rotating black hole, the Schwarzschild solution, technically has a region that could be interpreted as a bridge, the Einstein-Rosen bridge. But it's not traversable. It pinches off and you can't actually travel through and come out elsewhere. Any attempt to use a black hole as a portal meets the problem that you'd be crushed at the singularity. Rotating black holes, Kerr black holes, have more complex interiors in theory and could have pathways to other universes on paper, but these are not considered physically realistic scenarios, and any perturbation likely destroys the wormhole. So the common sci-fi trope of flying the spaceship into a black hole and popping out in some distant galaxy or alternate universe is not supported by our current understanding. As far as we know, if you dive into a black hole, it's a one-way trip to doom, not to Wonderland or a different time.
Nothing ever comes out of a black hole, not even light. They last forever. We've learned that this is not entirely true. It is true that nothing can escape from inside the event horizon, classically. However, people often interpret "nothing comes out" as absolute. Hawking's work showed that black holes can leak Hawking radiation, meaning over immense timescales, they evaporate. So in principle, black holes don't last forever. A very small black hole could completely evaporate on timescales of perhaps 10 to the 67 years, or much more for bigger ones. Now, Hawking radiation aside, there's also the fact that black holes are often surrounded by lots of energetic phenomena. As we discussed, they emit X-rays, jets, etc. from just outside their horizons. So they're far from quiet or totally dark in practice. Another nuance. Information and matter that falls in seems gone, but whether something truly nothing comes out is tied to that info paradox. The consensus is that black holes do emit something, Hawking radiation, and they will eventually vanish, possibly releasing some form of the information back, according to some theories. So they're not eternal prisons in the strictest sense. But it's correct that you cannot classically retrieve an object that has crossed the horizon. You can't get in there to pull it out. Finally, the idea that black holes last forever is wrong under Hawking's theory. Given enough time, even the mightiest black hole will radiate away mass, albeit we're talking time spans vastly longer than the current age of the universe for big ones. Black holes are extremely rare, exotic objects. They are exotic, yes, but not really rare in the grand scheme of the universe. As mentioned, our galaxy could harbor millions or even 100 million stellar black holes. Every big galaxy has a supermassive black hole. They're common outcomes of massive star evolution, and given how many stars are out there, black holes are plentiful. We don't need to look to the far reaches of the universe to find one. The nearest known stellar black hole is only a few thousand light years away. It's a misconception to think of them as mythical, singular entities scattered sparingly. The universe is likely teeming with black holes. They're just hard to detect and less feeding. So rare isn't the right word. Invisible or elusive might be better. There could even be a rogue black hole closer than we think, wandering between the stars in our galaxy. We've started identifying some candidates via microlensing. So black holes are a natural, fairly common end state for massive stars and a common component of galaxies. You can see a black hole sucking in matter in those pictures. When people see images like the EHT photo or artistic illustrations, some think that the black hole itself is the glowing thing. Important to clarify, we have never seen the black hole itself, the interior. What we see is either the accretion disk or the light being lensed around the black hole. In the EHT image, the glow is from superheated gas near the horizon. The black hole's actual disk is dark. In simulations or Interstellar's visuals, the swirl is light from the disk and lensed around. A black hole would appear truly black against a backdrop. The EHT used a bright backdrop, the hot gas, to make the silhouette visible. So, if you're picturing a black hole as a big vacuum with a literal hole you can see into, adjust that. It's an object that simply doesn't allow light out, so it would appear as a black sphere if set against anything bright. By dispelling these misconceptions, we get a clearer picture of black holes. They are not cosmic monsters hunting us down, but rather natural outcomes of gravity that follow the same rules as other massive bodies, just taken to an extreme. They can be prolific energy sources, paradoxically, since they're black, and while dangerous up close, they're an integral part of the cosmic landscape, not a fantastical anomaly.
Black holes, once purely theoretical curiosities, are now central characters in modern astrophysics. In this script, we've seen how they form from dying stars or cosmic collisions, how they come in different sizes from stellar to supermassive, and what defines them: an event horizon with no return, and a possibly mystical singularity at the core. We've discussed how scientists detect these invisible beasts through X-rays, stellar orbits, gravitational waves, and even direct imaging of a black hole's shadow. We've marveled at the extreme effects black holes have on their surroundings, bending light like a funhouse mirror, slowing time to a crawl, and ripping apart anything that ventures too close. Theoretical physics treats black holes as laboratories for the fundamental laws of nature, where puzzles like Hawking radiation and the information paradox hint at new physics beyond our current understanding. Perhaps what makes black holes so endlessly captivating is this blend of the simple and the mysterious. On one hand, a black hole can be described just by mass and spin, and we now have actual pictures of one, confirming they're real. On the other, they represent the edge of knowledge, places where space and time as we know them cease to function normally. They force us to ask big questions about the universe. What happens at the limits of gravity? How do we unify gravity with quantum mechanics? Is information fundamentally conserved? Black holes sit at the nexus of these questions, motivating new research every day. The story of black holes is still being written. With each new telescope and detector, from next-generation gravitational wave observatories to more advanced radio arrays, we peel back another layer of the mystery. We might witness intermediate mass black holes being caught in the act, or detect the faint hum of Hawking radiation one day, or finally settle the information paradox through theory or experiment. Black holes have gone from mathematical solutions in Einstein's equations to concrete objects we study in the sky. They have even entered pop culture, inspiring countless movies, novels, and imaginations. In closing, black holes remind us of nature's capacity for the sublime. They are a testament to gravity's power, capable of creating something as astonishing as a point of no return in the fabric of the cosmos. Yet, rather than merely being destroyers, black holes also illuminate, energizing galaxies, forging heavy elements in neutron-star collisions that make black holes, and pushing the frontiers of science. As our understanding grows, black holes continue to be a source of profound wonder and excitement. They show us that even in darkness, there is much to learn and light to shed. The journey to understand black holes, much like falling into one, is an adventure into the unknown, and we can't help but be pulled in by their gravity.